don't know.
We'll see. Okay, hi everyone. Welcome back. So it is my pleasure to introduce Ward Beullens, who's a postdoc at IBM Research Zurich. So he will tell us about Rainbow and more broadly about MQ signatures. So I want to remind everyone that we have a Zulip chat, and so there is a special section on Zulip dedicated to this invited talk by Ward. So if you have questions, please put them on the correct Zulip section. Okay, so Ward, the floor is yours.
Yeah, thank you very much. The official title is about breaking Rainbow. But yeah, I decided that talking about Rainbow for an hour would maybe be a bit much. So I'm going to talk more broadly about an overview of state-of-the-art of multivariate signatures. But I have to warn you that it's going to be quite biased. I'm mostly going to talk about the schemes that I like very much and the schemes that I worked on. So if I don't talk a lot about your favorite MQ scheme, then I apologize. But yeah, I can't talk about everything. So this is the family tree of the multivariate signatures. So on the left, you have the pure MQ signatures. So these are signatures that rely only on the hardness of the MQ problem. So this is just a problem where you're given like uniformly random multivariate quadratic equations, and you have to find a solution. And we strongly believe that this is a hard problem. It's it's NP hard. The schemes that I built on this problem alone are believed to be secure, and in particular, none of them have been really badly broken. The drawback of this strong security guarantee is that they're not super efficient. I think the best one at the moment has signatures that are 9 kilobytes big. And this is very similar to Sphinx, Sphinx Plus. So, if we're honest, then we should just use Sphinx instead of these MQ schemes. But these MQ schemes have been improving a lot. So it's interesting to see if we can keep improving and get something that's more practical in the end. But this is not really the topic that I'm going to talk about today. I'm going to talk more about these trapdoor signatures. So here, you don't rely on a random multivariate system, but some trapdoor system. And so we not only require that solving random systems is hard, but also that somehow you can trapdoor them in a way that doesn't lose security. I think there's two families of trapdoored MQ signatures. There's on one hand the oil and vinegar-like schemes. So sometimes these are called small field schemes because they work over a small field. And I think the first scheme in this family was oil and vinegar. This was invented in 1997. And then later there were more schemes like Rainbow, which was one of the finalists of the NIST competition. And then lately there's Mayo. And yesterday we heard about IP Rainbow, which also fits in this family. And then the other family is hidden field equations like signatures, or maybe I should say C-star like, because C-star was the first scheme in this family. And these have a much stronger algebraic structure. Like typically your multivariate map encodes some kind of univariate polynomial over a big field. So this is why they are called big field schemes. But yeah, here the structure is much stronger and more difficult to hide, and this is why most of these schemes, if not all of them, are broken. And it seems to there's still some schemes I think, but they're very very slow. This branch seems to be a little bit less successful, in my opinion. I hope I don't offend anyone here. So today we'll mostly talk about this family in the middle, the oil and vinegar like signatures. And I'll talk about oil and vinegar, Rainbow, and in the end I'll talk a little bit about Mayo. Okay, so yeah, let's start with oil and vinegar. I already mentioned that it's based on a trapdoor. So the public key is going to be this map P, which is a multivariate quadratic map in a number of variables. So here's an example. So it's just like a number of multivariate quadratic polynomials over some finite field. This one has 3 polynomials in 3 variables. And this trapdoor function is supposed to look random, which means that finding preimages for this function is going to be hard, because we believe that the MQ problem is hard. But actually, there's some hidden structure inside this P that if you know this structure, then you can solve for preimages. So if I give you a y, then you can solve for an x such that p of x is equal to y. Right? And if you have this, then you can try to make a signature scheme out of this. This is exactly how RSA signatures work. Right? Your RSA function is your trapdoor function. The secret key is like your factorization of your RSA modulus, and this allows you to sample preimages, and then you can sign. Right? So here's exactly the same thing, except instead of this exponentiation modulo your RSA modulus, you have this multivariate map P. Right? So if you want to sign a message M, what you do is you hash the message to fq to the m, so your output space of your function, and then you use your trapdoor information to produce a preimage, and this preimage is going to be your signature. Right? So your signature is an x, so that p of x is equal to the hash of your message. So really, the question is, how do I trapdoor these multivariate quadratic maps? And one way to do this, a very nice way, if you ask me to do this, is with the oil and vinegar construction. Right, so here, your trapdoor structure is a linear subspace O. We call this the oil space for mysterious reasons. And the dimension of this space is going to be equal to M, which is the dimension of the output space. Right? And what's special about this space O is that your function P vanishes on this space O, right? Meaning for every vector O in the space O, you have that P of O is equal to 0. And that's it. So that's all the structure you have. And it turns out that if you know such a subspace, then you can efficiently sample preimages. But before I can explain how to do that, I need to introduce this definition of what's called the differential. So if you have a multivariate quadratic map, or really any function, you can define this differential at x, where x is an element of your input space, as this function here. So it maps y to p of x plus y minus p of x minus p of y. And this is an interesting function because it's linear in both x and y. Right? You can easily check this yourself. And if it wasn't linear, then differential would be a bad name, because usually like the differential of something quadratic better be something linear, right? Otherwise the name is not very good, right? But yeah, this is very easy to check, and it turns out that this is a very useful tool to construct schemes, but also to cryptanalyze schemes. Right, so with this tool, I can explain how you can use this trapdoor space O, this oil space, to sample preimages. Right, so we're given this output y, and we want to find a preimage, so we want to find an x so that p of x is equal to y. And so how do you do this? You just start by picking a random input v, and of course this input is not going to be a solution, but you can try to solve for a vector O in your oil space such that p of v plus O is equal to the target that you're aiming for, is equal to the y. And this turns out to be easy, because like using our definition of the differential, we can write p of v plus O as p of v plus p of O plus the differential at v of O. But we chose O to be like a space on which p vanishes, right? So we can cancel this middle term, and then what's left is just p of v, which is some constant, and this differential, but this differential is linear in O, right? So what's left is just a linear system of equations, right? We have m equations because p has m components, And we have m degrees of freedom, right? Because the space O has dimension m. So this means that with high probability, we can this system will have a unique solution, and you can solve for it. And then once you have O, you just output V plus O, right? But of course, it can happen with a small probability that this linear system of equations does not have a solution, and then you just try again with a different choice for your vector V. Right. So that's how the trapdoor works. So yeah, I hope I could convince you that this is a really elegant construction. That your trapdoor structure is just one linear space O on which P vanishes, and that's it. Yeah. So how do you choose secure parameters for this thing? Well, very loosely speaking, you need two things. Like one is that finding this Euler space O should be hard, and secondly, if you don't know O, then it should be hard to forge signatures. Right? So hard to find X, so that P of X is equal to the hash of your message. And these two constraints translate to two requirements on your parameters. This first thing, that key recovery should be hard, means that the n, which is the number of variables, should be much bigger than m. Right? Go back here. So n is the dimension of your input space, and m is the dimension of O. So kind of intuitively, it makes sense that n should be big enough to hide O. Right? If you're hiding a needle in a haystack, then you want your haystack to be much bigger than the needle. Otherwise, it's going to be easy to find the needle. Right? So that's the intuition. And yeah, the attacks that we have, they work in with complexity. Like the first attack on this problem had complexity q to the n minus 2 times m. So if your number of variables is 2 times the number of equations, then you have a polynomial time attack. But as soon as n starts growing beyond 2m, then the attack becomes really expensive. And nowadays we have like better attacks, but they still have this behavior that like for n equals 2m, the attacks work in polynomial time, but then the attack quickly becomes much more expensive. So that's one requirement. N should be bigger than 2m. And the second requirement is, yeah, you just want the MQ problem to be hard. And that means that the number of equations should be big enough. So yeah, this n here should be an m really, but yeah, doesn't, yeah. So for the MQ problem to be hard, we need m to be big, and then for the key recovery to be hard, we need n to be sufficiently larger than m, so at least a factor 2. And yeah, if you choose on parameters, you could get the numbers in this table. These are two instantiations for NIST security level 1, and these are also the ones that we are going to submit to the NIST competition. And so yeah, you can see the public key sizes are kind of big, like 66 kilobyte or 43 kilobytes, but yeah, the signature size is quite small. Like wait, I think this 69 is supposed to be 96. Sorry. And then 128 bytes for the other parameter set. Yeah, maybe if you're paying attention, you might think, wait, this 66 kilobyte, that seems too small, because your public key is this map P, and this P has 64 polynomials, and each polynomial is quadratic and 160 variables. So like a single polynomial is gonna have like 160 squared divided by 2 coefficients, and you need to do this times the number of equations. So this is going to be bigger than 66 kilobytes. But yeah, this is because like most of your public key is going to be random. So you can just pick a seed and then expand the seed to get a lot of coefficients of your map P. And then during key generation, you just solve for the remaining coefficients such that P vanishes on your secret space O. Right? So I think like 90% of the map P you can expand from a random number generator, and then only the remaining 10% you have to really communicate as your public key. Right? So this is why the public key size is smaller than you would expect, but still kind of big. Okay, so I think that's what I wanted to say about oil and vinegar. Yeah, now we move on to Rainbow. So yeah, Rainbow, a little bit of history. So it's based on the oil and vinegar scheme, which I mentioned was invented in 1997. Rainbow came in 2005, and it's meant to be like a variant of oil and vinegar that is a bit more efficient in terms of speed and in terms of signature size. So after the invention of Rainbow, there was a lot of cryptanalysis, but like it dried up after like a few years. And since then, nothing really happened until Rainbow entered in the NIST competition. And then, yeah, people started to pay attention again and improved mainly the old attacks. And yeah, there were some advances in the min rank problem. And one of the ways to attack Rainbow was through this min rank problem. So this improved the attacks a little bit. And also there was this rainbow band separation attack, which was known long before, but it turned out that the attack improved a little bit better than was known. So there were some results here, but yeah, there were not really any new attacks on Rainbow, and yeah, then things started to go wrong in 2021 when we had a new description of how Rainbow works. And this, better understanding of what's really going on led to some new attacks. And then, like this year, there was like a new attack that actually works very well in practice and is able to break the security level 1 parameters of Rainbow in practice. Right, so that's what I'm going to talk about a little bit in the coming minutes. But first, okay, yeah, some parameters. So the first two columns are the oil and vinegar that I talked about earlier, and Rainbow in comparison is a little bit more efficient, right? The signatures are only 66 bytes instead of like 100 or 120 bytes. And also the number of variables in your system is a little bit smaller. It's only 100 versus like 160. And this is good for the efficiency of your signing and verification, right? Because if your map is smaller, then it's going to be faster to evaluate it, right? So Rainbow is a bit faster and also has smaller signatures. And that's why Rainbow was submitted to the NIST competition and not oil and vinegar. Okay, so the trapdoor structure of Rainbow is a little bit more complicated than that of oil and vinegar, but you still can explain this in terms of some secret spaces, right? So with oil and vinegar, you only had one oil space, and now with Rainbow you have two. You have O2, which is included in O1, which is a little bit bigger, and you also have a secret space in your output space, which we call W, and then your public key P is a map that behaves in some nice way on these secret spaces. But in particular, P vanishes on the small oil space. So for every vector in O2, P of that vector is going to be 0. P sends the O1 space to W. And also the third property is that for any vector X, the differential will send this space O2 to the space W. So this sounds a bit ad hoc at the moment, but this is really exactly what you need to like generalize the signing algorithm from oil and vinegar to Rainbow. Again, this is for Rainbow with 2 layers, but you can generalize this to Rainbow with many layers, and then you just have longer chains of subspaces. Like here we only have O2 in O1, but these chains can be arbitrarily long. But yeah, the parameters that were submitted to NIST only have 2 layers, so that's why we focus on them here. Yeah, so I'm not going to explain how to do signing or sampling pre-images for this, but yeah, it's not too difficult. Basically, yeah, the idea is to use the oil and vinegar strategy twice. So first, you pick some random input V, And then instead of like solving for something that immediately gives you a pre-image, you do it in 2 steps. So first you solve for some correction factor in O1 that makes your image correct up to some vector in W. And then after you did this, you solve for another linear system to get a correction term in O2, such that you have an exact pre-image. Right? So it's kind of 2 steps of oil and vinegar. But yeah, if you're interested in this, you should read the paper. So yeah, the main attack, the main idea of the attack is going to focus on this property involving the differential. Right, so I'll just repeat. So for every vector in the input space, we have that the differential at x. So this is what this thing defined as the map that sends y to p of x plus y minus p of x minus p of y. This linear map sends O2 to W. So these are 2 of our secret spaces. And yeah, from this property, we want to recover a vector in O2. And yeah, the way I did this in my paper in Eurocrypt was to observe that this reduces to some min-rank problem. But actually, it turns out that there's a much more direct way of finding vectors in O2. And that's with the observation that these differentials are likely to have a non-zero kernel vector that sits in O2. So why would that be? Well, if this differential is just a random map that sends O2 to W, then for every non-zero vector in O2, you have a probability in 1 over the size of W that it maps this vector to 0, right? And you have the size of O2 candidates. So the average number of non-zero kernel vectors is going to be 1, because the dimension of O2 is the same as the dimension of W, right? So the average is 1. But doesn't mean that with probability close to 1, you'll have a non-zero kernel vector, because like as soon as you have 1 non-zero kernel vector, then all the multiples will also be in the kernel, right? So they come in clusters of size q minus 1, right? So the probability of having a non-zero kernel vector is close to 1 over q minus 1. So yeah, this is a very heuristic explanation where you can like calculate this more precisely, but yeah, this is just the observation, right? So for every x that you pick, this differential at x is will have a non-zero kernel vector in O2 with a reasonably large probability, like 1 over q. And yeah, with this observation, the attack is really simple. So you just guess a differential d of x. You hope that it has a non-zero kernel vector in O2, and then you just try to solve for this this vector if it exists, right? So you're just solving this system where d of x, dx of O is equal to 0. This just says O is in the kernel of dx. And then this second equation, P of O is equal to 0. Yeah, this is satisfied for vectors that are inside of our oil space, right? O2, because that's kind of the definition of O2, was that P vanishes on O2, right? So by just solving this system of equations, we can hope to find the vector O if it exists. And yeah, this is quite efficient because this first set of equations are just linear equations, so we can use them to eliminate a lot of variables in the second set of equations, which are quadratic. And so you have a system of quadratic equations that's not too big, because we were able to eliminate a lot of variables. And then you can just use like standard techniques to try to solve the system. And then yeah, if you find a solution, then you're basically done. Okay, I did this with a Wiedemann Excel algorithm, for which there was an optimized implementation that used by Ruben Niederhagen and his co-authors. And yeah, I mentioned the probability that this vector exists is roughly 1 over q, q minus 1, and q minus 1 is equal to 15. So on average, we have to repeat the step 15 times, and each step takes like 3 hours and a half. So in expectation, the attack will take 53 hours, which is 1 weekend if you count the Friday evenings as part of your weekend. Okay, so, oh yeah, and how do you finish the attack? So I told you this is how you get a single vector in O2, but then as soon as you know a single vector in O2, then everything like collapses, and finding the entire secret key is kind of easy, right? So the first step is you again use this property of the differential. So you know this vector O, and then you just try random x, and d of x of O will be inside of W, right? So you just do this for many x until you have a basis for W. And then once you know all of W, you can again use this property to solve for all the vectors such that d of x of these vectors sit inside W for all x. So this is just solving a linear system, and this gives you all of the vectors in O2. And now, we know W and O2, so the only thing that we still need to find is the space O1. And the way to do this is take a quotient by O2 and by W, right? So you have to check that this quotient is well defined, or no, you have to check that this P is still well defined on the quotient. But this is the case because if you change your input by a vector in O2, then the output will change by a vector in W, right? So your probably key is still well defined on this quotient. And then like what remains after taking the quotient is exactly like an instance of the oil and vinegar scheme, right? So you just have like a quadratic map P on some space, and it vanishes on some other space, which is O1 divided out by O2. And then we want to find this O1 thing. So this is exactly the same as in oil and vinegar. So you can just use existing attacks on the oil and vinegar schemes to recover O1. And this is going to be easy in this case because the space is now quite small because you took a quotient that removes a lot of variables. So you get an oil and vinegar instance that's not secure because it's too small. Okay, so that was how you finish the attack. And I mentioned the attack is very efficient. You can do it in a weekend. You could keep Rainbow alive by changing the parameters because the attack is still exponential. But there's really no point in doing this, at least in my opinion, because if you go to new parameters, then like the public key size will be bigger than the public keys of oil and vinegar. Also, the signatures will be bigger. So you should just use oil and vinegar instead because it's much nicer, it's much simpler and more efficient. So but to be fair, I should say that maybe these parameters here for Rainbow are not optimal. I just took the old security level 3 parameters, but you can probably do a little bit better. But still, it's not going to be more efficient than oil and vinegar, right? So that's why we will submit oil and vinegar to the next signature competition of NIST. Okay, so I still have some time left, so I can talk about Mayo. So Mayo is another multivariate signature, and it's also based on oil and vinegar. So we have this starting point again. So you have this map P on n variables, and it vanishes on some secret space O, this oil space O. And the idea of Mayo is that it would be really nice if we can make this oil space smaller. This has two benefits, right? If the oil space is smaller, then we can also make n smaller, because n just had to be sufficiently larger than the oil space to hide it, right? So the needle got smaller, so the haystack can also be smaller. So this is nice because then if you're working with smaller maps, then everything gets faster. But also the public key becomes smaller because, like I mentioned, that you can generate a large part of your map P from a pseudo-random number generator. And if your oil space becomes smaller, then the part that you cannot generate also becomes smaller because your map P is more random in some sense, so you can generate more of its coefficients just from a pseudo-random number generator. And this means the public key becomes like O squared times m instead of m cubed. Right? M is the number of components of your map P. So let's say if O is like a factor 10 smaller than M, then you win a factor 100 in the size of your public key. So this can really make a big difference, right? So this is what we're going to try to do. But yeah, why doesn't oil and vinegar use a small O? This is because the signing algorithm fails if you try to do this, right? If you remember, the way signing works is you pick a random V and then you solve for an O, so that P of V plus O is your target. And this turns into a system of linear equations. The number of equations is M, and the degrees of freedom is the dimension of this oil space, right? So this is why in oil and vinegar we pick the dimension of the oil space to be equal to M, because yeah, if the degrees of freedom are less than the number of equations, you will with very high probability not have any solutions, so you cannot sign any messages. So this is the problem that we're going to work around with Mayo, and yeah, the idea is quite simple, I think. So we're going to start with a little bit of oil and vinegar with like an oil space that's too small, and then we're going to try to whip it up and make it like bigger in such a way that the oil space also gets made bigger, and you just like increase the number of variables by some factor factor k in some way, such that k times the dimension of O is bigger than M, and then you can sign, right? So I hope it gets clearer when I give like an example. So a naive way of doing this is to define your bigger map P star in this way. So P star of x1 up to xk, we just define it to be P of x1 plus P of x2 all the way up to P of xk. Of course, yeah, if you do this, the number of variables goes up by a factor k, but the dimension of your oil space also goes up by a factor k, right? Because you have a new oil space, which is just k copies of O, and of course, this map P star will vanish on this space, right? If you plug in like oil vectors for all these copies of P, that they will all the terms will be 0, and your P vanishes. P star vanishes on this bigger oil space K. Okay, so you just need to pick parameters such that K times O is bigger than M, and then we can sample pre-images for P star, right? So we can have a signature scheme. Unfortunately, this approach is a little bit too simple, and the reason for this is that this P star has extra oil spaces, so extra spaces on which it vanishes. For example, if I is a square root of -1, so we assume this exists in a finite field, then like this space that consists of vectors x, ix, and then zeros is going to be an oil space, because P star of such a vector is just P of x plus P of I times x. But P is homogeneous, so this I, you can take it outside and it becomes an I squared, which is -1. And then you get P of x minus P of x is equal to 0, right? And like the problem is that the attacker, he also knows that this is an oil space, so he can just use this space to sample pre-images, meaning that this P star is not going to be pre-image resistant, right? So I think of this as you try to whip up oil and vinegar and mix it and make it bigger, but of course oil and vinegar, it doesn't mix well, so it just collapses again and you don't win anything. So the solution is of course to add some eggs to bind the oil and the vinegar to make a nice homogeneous sauce. And yeah, so the way we do is we add these egg matrices. We pick k matrices, and we define this P star map as E1 times P times x1 plus ... up to ek times P of xk. And yeah, if you do this, you can analyze this, and then the chance of having an extra oil space is negligibly small. So this solves one problem. There's still a problem though, which is that this P star is a sum of k functions with independent inputs. Right? So if you want to find a pre-image for this function, then this is like a k-sum problem, and there are generic attacks that solve this with some complexity which is exponential, but like not as big as we would hope. So there's two solutions. Either you just accept that these attacks exist, and then you pick parameters such that this attack complexity is very big, or the other approach is to add some other terms to your P star, some cross terms that involve like xi and xj to break this k list attack, right? And you can do this in this way. So you pick some more egg matrices and you add some differentials. And this seems a bit ad hoc maybe, but it prevents this k-list attack. Right. So the point is that we started from this small map P, and then we just mix it up into something much bigger with an oil space that's also bigger, so big enough to sample P images, right? So we just use this P star now in the same way as we used P in the original oil and vinegar construction to sample P images. So is this secure? Well, you can prove that it's secure under two assumptions. So the first one is that these oil and vinegar maps are indistinguishable from random maps. And it depends on what you believe, but I'm kind of happy with this to take this assumption because oil and vinegar has been around for almost 20 years. So this is kind of well studied. It's a very simple problem. You just have a bunch of multivariate quadratic equations that vanish on some oil space, and the problem is to find this space. And then the second assumption that you need is that this whipping of this map P is secure. Like if you start from a random map P and you make it into a bigger map P star, we're assuming that this P star is still pre-image resistant, or actually multi-target pre-image resistant. So this is very ad hoc. So this is an assumption that requires more cryptanalysis, I think. So I hope more people try to break this assumption or prove that it's secure, but I think that's going to be difficult. Right, and under this assumption, you can prove that the Mayo signature scheme is unforgeable, and like in particular, we can prove that by signing messages, you don't leak information about the secret key, and this is a bit special because you cannot do this for the normal oil and vinegar signature, and the reason is that sometimes you try to solve for this for a solution, but your system of linear equation doesn't have a solution, and you have to sample again, try again with a different V. And by this resampling, you can introduce some bias to the distribution of the signatures that you're giving out. We cannot argue that this information theoretically at least leaks some information about the signature, about the secret key. But we can prevent this with Mayo by just making the dimension of our oil space bigger than M. So now you're solving a system of equations where you have more degrees of freedom than equations. So with a huge, overwhelming probability, there will be a solution. So you can just pick a random solution. And in this way, you can prove that your signatures don't leak any information about the secret key. So that's another nice property of Mayo. And it's also nice from a practical point of view because you'll never have to try again with a different choice of V, which means that the running time of your signing algorithm is constant. Instead of for oil and vinegar, you have a lot of variability because sometimes you have to start over and Okay, so these are the parameters that you can choose. So you have a lot of freedom because you can choose the dimension of your space O. So here in this table, I gave two parameter sets, one where the dimension of O is 19. And in this case, this is pretty big, so you're close to the original oil and vinegar scheme. And in this case, the public key size is 6 kilobytes, and the signature size is 174 bytes. And if you use a smaller oil space, then your public key is going to be smaller, but the signature is going to be bigger, right? This is because you'll need to have to do more whipping, so to say. Like this map P will have to become much bigger to make the O space big enough. Like, and this means that your signature, which is a pre-image, will also be bigger, right? So this is why, in this case, like the signatures are also half a kilobyte, same as the public key. But this is still quite good, right? It's very similar to Falcon and like the recent variants of Falcon that are more compact. So yeah, I think this is nice. So yeah, I'm also going to submit this to the next NIST competition. And yeah, this brings me to the last slide. So I'm looking for people that want to help me with this. So there's if you think you can help, like with design, if you have a nice idea that make things more efficient, or like if you think you can help in any way, please reach out to me, because we're making a team. So far, it's just me, Sophia Shelley, and someone else. But yeah, if you think that you can help in any way, like implementation, security proofs, side channel security, or if you just have sauce-related puns that can make it into the submission somehow, please reach out to me. For example, like Dilithium and Kyber, they have this 90s version where you do the expansion of your seeds with AES. So we're also going to do this with Mayo, but then of course we call it Mayo and AES. That's the name of this variant, right? So I think I'm going to stop here. So thank you very much for your attention.
Thank you, Ward, for the very nice talk. Very enjoyable, and I learned plenty of things. For those who are listening, so if you have questions, don't hesitate putting them on the lip. So for the moment, I don't see any, but so I have a couple of questions. So you have time to write your own. Okay, so about Mayo, so this I found very interesting, that you can trade the verification key size for a bit larger signatures, and the trade-off is very good because the VK size decreases very fast. Yeah. Can you go beyond, like decrease the verification key size even more, up to some increase of signature size? What is the limit of this?
Yeah, you can definitely go more. But yeah, that's not really useful. I think in general, it's not useful to make the public key. Like you can always do this for any signature scheme, right? You just replace your public key by a hash of your public key, and you put the real public key as part of your signature, right? And then in verification, you just check the hash of your public key, and then you check that the signature is valid, right? So. I mean, yeah, you can do it, but I don't think it's particularly. Okay,
so let me phrase a less stupid question then. So if you want to minimize VK size plus SIG size, what's the best?
Yeah, I think this parameter is close to optimal in that sense. So both public key and signature are close to half a kilobyte, and this is very similar to Falcon and these other variants.
Okay, thanks. Yeah, then I had a very naive question also on the first half of the talk. So from what I understood, having several layers of oil, so this was tempting as a way to reduce, to make the scheme more efficient. But what you showed is that it's just making the schemes more inefficient. So there is no point doing this anymore. Is that a correct understanding? Okay.
Yeah.
Okay, thanks. So I have a practical question on the lip by Mohamed Gundogan, sorry for mispronouncing. He's asking whether you can share the slides, and he's thanking you for the great talk. So
I can definitely share the slides. I guess I'll just send them to Tanya and she'll take care of it.
Yeah, I guess so. I see that the other invited talks, they have their slides on the program webpage. Okay, thanks. And maybe another very naive question. So when you mention algorithms, so it's mostly from what I understood, it's classical algorithms. What about the quantum cryptanalysis landscape? What is there something interesting happening here, or it's just Grover, or what?
So there's two problems. Right? First is the key recovery, and I think on this side, because this is very specific to vinegar, I don't think anybody has tried to come up with a nice quantum algorithm that is smarter than just doing Grover for some part. So here, I don't know of any quantum cryptanalysis except for Grover. And then the other part is the pure MQ problem. And there, I think only for the binary case there was something interesting. Like if you just use Grover in the binary case, then you have the square root of 2 to the n, right? This complexity, so 0.5n, and I think you can do a little bit better. Was 0.47n or something. So you can do a little bit better than Grover, but not very much, right? So as far as you know, the quantum attacks are not really much better than classical ones.
Okay, thanks. So I don't see any other question on the lip. So I'll just thank you again for this great talk, and wish you good luck for your next submissions.
Thank you very much.